Alright, hell yeah. Alright, so this video, the fun part's at the end, but you know what I mean? Stay tuned for all the equations that get there. Anyway, have a good time. Alright, hell yeah. So we have material mechanics, we got some chunks of steel here, because this is going to be a cool video. We're going to go over all the things that can happen with steel. You know what I mean? Material mechanics is such a maybe complex, you know what I mean, thing that you're just like, well, how many things can happen? So we're going to do this example where we have it like an engine block on a table, and we're going to say that, hey, this is like a beam, and it's going to bend like this. This is a column, and so we have something about columns where if they're too tall, you ever see someone with like a huge deck, and then they just have something like just just like a 4x4, just supporting like a whole party full of people. That's insane. But anyway, the fact that it gets so long, it turns into like a bow, you know, like an archer's bow, where it'll just collapse in on itself. And so I guess that picture is right here. So that's columns. You can have torque on stuff. So on the engine block, we're going to have a bolt, and we're going to torque it because it's stuck. And we want to know how much pounds we can try to get it unstuck before we're like, oh hell no, we're just going to break that head right off. And then and then you have the classic, you know what I mean? I always bring out my cheat sheet. You know, we have, hey, strength is force over area, change in length. But for this one, all you need is kind of two. Strength is force over area, and then shear. And you're like, well, are we going to shear this bolt? No. But when you put this weight on this engine block, hey, the connection right here is welded up, and that might just shear, you know, it might just drop out. And so the area that's holding on, that's going to be in shear. So now, just from one problem, we can kind of analyze everything. And we're going to show that we don't have to make this too complicated. I go to the example of like, hey, if you were trying to find the area of a circle, don't you just know that's like pi r squared? You know what I mean? Pi d squared divided by 4. That's it. You know what I mean? You don't need to watch that YouTube video on like slices of pizza and try to, how do we integrate to here? It's like no one cares. And that's the thing with material mechanics. It is like almost at a level, like you don't trust the equations. You know what I mean? You're just like, well, I got to apply a lot of theory and start from the fundamentals. And the fundamentals just basically say, hey, you can put force on stuff, but then guess what? If you change its shape, if you have like stuff with different shapes, like look at this, you get like, you know, big leverages going on. So material mechanics is like, hell yeah, you know, you can only put so much force on the molecules of steel, but then you have certain situations where you get hella leverage, and then what? You know what I mean? Well, we know like a bridge can't take much weight compared to just, you know, having this. I mean, let's just run some calculations. Because we have this term for strength, it's 58,000, that's what I use for steel, and we want to know how much compression we can put into this. Or if we were trying to hang something, you know, I can't hang a semi from this, but I could get pretty close. Can't hang an empty semi from that, but or you know, but how much? So what is the area of this? This is a thickness of 0.083. And so we have, hey, well, what's the perimeter? This is 2 inches, so we got 8 inches. So we got 8 times 0.083, so that's the area. Strength times areas, because strength is in pounds per inches squared. So 58,000 pounds per inches squared, multiplied by that area. And we get a force right off the bat of 38,000. So I take it back. An empty semi might only weigh like 40,000. And that's with an empty trailer. So you definitely could just weld this to the top of a semi cab and then just start lifting. You know what I mean? Probably the roof of the semi won't hold. All right, but you know, that just kind of gives us an idea of what we're dealing with. And let's get this to this side. So yeah, force over area. And then shear. So what are we talking about in shear? Well, honestly, you know what I mean? Hey, they say that for steel, shear is just the strength, the tensile strength divided by 2. Well, what the hell? You know what I mean? Why don't you just turn this equation into strength is force divided by, you know, 2 area. Or strength is just 1/2 force divided by area. You know what I mean? Because then, you know, and we all know that the shear force is, obviously it's going to be that direction. Cool, it's perpendicular. I don't think we need like a whole nother letter to signify that. But, so anyway, so it's just fascinating that you can make such simple changes where you could bring equations to the natural world. And so anyway, so we have, we need to find the force. We'll rearrange all that. 2 and A are going to go upstairs. 2A strength is equal to force. Cool. So now we just have that area. Whoa. I feel like we did something wrong. I said this was, sorry. This is strength divided by 2. There you go. So now if we wanted to, here's our relationship. We wanted to find force. Area goes upstairs, and we got 1/2 strength times area, obviously. So that 38,000, you know what I mean, easy peasy. We just divide by 2. And so if you drove a car on a cantilever on this, and this is what was holding as just a single cantilevered bridge, you could put 19,000, so you'd weld this. That's amazing. And then if you sheared it, you know, if you welded this to a wall and then started hanging something, you can't hang that cab of that semi, but you can hang 20,000 pounds. That's amazing. All right, so that's 2 equations down, and we got 1, 2, kind of 3 more to go, and that's it. That's material mechanics wrapped up in a nutshell. So for beams, you know what I mean, you will not find this equation, you know, spelled out, because it's already with the moment. I think there's like a sigma is equal to moment Iy. You know, I don't even care. You know what I mean? You can just, it's like, why derive things? Why get them in such basic form when, you know, it would be like if the area of a circle was more complicated than that, you'd be like, oh hell no. So this says, you know, if we have a beam that's this long, and we have the strength of steel, 58,000. Now we need to know something about its shape. So this is I. And so now we're going to take a little tangent, because this also could be 4 sigma S divided by L. And let's back off for a moment. This is going to be a beam that is not welded to the sides. It's just kind of resting on like 2 2x4s, you know what I mean? And so that's what this is. If you do have it like rigidly welded, or you know, in a structure like a building, hey, you can turn this into 8. If you have a cantilever, oh hell no, it goes to a strength of 1. You know what I mean? So that was easy. And what this basically says is like the force of the beam, if the length goes up, hell no, you can get way less strength. You know, so longer the length, the crappier the bridge. You know what I mean? If you're just still using the same material. So now this is the strength of steel. Now this I is just a shape. Just look at it. It looks like the shape of an I-beam. But then you have to divide by the height of half the height of the I-beam. So this Y is half the height of the I-beam. Hopefully I got that right. But anyway, or you can just say it's S, because this is something you look up in an I-beam chart. So you go to the steel yard and you're just like, well, I want to drive my car. So even in tons, you know what I mean? Well, how many tons is a car? You know, let's say 3, but we want to go 4 tons. I want to drive a 4-ton car. But actually, I'm just going to use 2 I-beams. So I just need 2 tons, like, it's going to be, both tires are going to be on both I-beams. So I just need 2 tons here. So there you go. So now I need to actually figure out what the shape of my I-beam is. So I'm going to go to this equation. I'm going to put 2 right here, and then the length in inches. Well, let's say it's, just 100 inches. So I'm going to go, so I need an S of 2, which is really, and then you just look up that chart and be like, hell, that's my I-beam. And that wouldn't be too big of a deal. You could just imagine, if you're only going 10 feet, and you had chunks of steel that were shaped as an I, for 10 feet, you could kind of visualize a car driving over that. So even just doing that's going to be hugely important in just like sizing things up, because when it comes to material, we all do this. We go to the hardware store and we're just like, yeah, that should work. You know what I mean? And that's the crazy thing about material mechanics, is you have so much theory, and they don't even spell out the useful equations. So even this is like, hey, if I had, like right here, if I was building something out of wood and it was square, if it was square, I just throw in this one of the sides, multiply by 3, I mean, power to the 3, and then here's my length, and I could find the force of that beam, you know what I mean? So I just turn these off. This is a 2x4, you know what I mean? This width, if it's flat like this, well, I hope this equation's right, you know what I mean? And hopefully it's like that. But anyway, you would do 3.5 by 1.5 squared, and then divided by, you know, if it was 16 feet, 16 times 12, 192. So we can do this. I'm going to see if I could get one of the longest, you know, 2x4s. Can you even get a 2x4 that's 16 feet long? Probably not. But you can at least get a 2x4 that's probably 10 feet. You know what I mean? So let's just do that. Let's do 10 feet. So we're going to go 16.6 times 3.5? Yeah, for a 2x4. Times 1.5 squared. And then we're going to divide that by 10 times 12. We're going to do 10 feet. And, oh, why didn't this work? Let's try again. 16.6 times 3.5 times 1.5 squared, and divided by, damn it, you know what I mean? That's the deal with, yep, my equations are bad. Anyway, that's the nature of it, you know what I mean? Oh, that just trashes this video. It's like, how do you move on, you know what I mean, when this equation doesn't seem to work out with reality. But anyway, so yeah, let's put that aside, because yeah, I gotta recheck that. But anyway, but this will work. So if we want to find the bending moment of this beam, but we do need this I. So I for steel, this could be a pretty easy one to remember. It's and if it's solid, if it's a solid square, it's going to be a to the 4th divided by 12. So this area moment of inertia is like inches to the 4th. And, okay, but if we have something that looks like this, you have to take the outside diameter, 2, so it's going to be 2 to the 4th divided by 12, but then there is no inside part, so you actually have to subtract that, so that's going to be like maybe b to the 4th divided by 12. And that is going to be, if the thickness is 0.083 times 2, and then we're going to go 2 minus that. So now we have this stored as alpha b. You know what I mean? So now we have 2 to the 4th divided by 12 minus, and then we have alpha b to the 4th divided by 12. So now we have 0.39, you know, 0.39, and this is inches to the 4th. And this is the thing with material mechanics, you know what I mean? Doing something to the 4th and then kind of getting a small number, you know what I mean? But I just know that for 2-inch steel, this is one I do all the time. So you should always have checks on reality on your equations to be like, hell yeah, I throw this in and I'm always going to get 0.3905, you know what I mean? So that's cool. And then I could even do it for these two. And I guess we'll do that right now. So this is a little bit thinner. It's like a 1/16 of an inch. And the steel yard is 0.063. And it's just like, wait, where does that come from? You know, where does 0.063 come from? Well, let's take a half. Divide by 2 is 0.25. Divide by 2 is 1.25. Divide by 2 is 0.06. See how that 12 becomes a 6? And then this becomes 2.5. And guess what? We just round to 0.063. You know what I mean? So just in the steel world, you're just like, why am I always calling that 0.063? And that's just kind of what I reference. You know what I mean? Instead of just thinking, oh, no, it's just a 1/16 of an inch. All right, so let's do this. So we have this is 3/4. So this video is also going to be, and I'll probably have to make an addendum at the beginning. We're going to stand on some steel. It's going to be real lackluster, but I'm just going to make sure I get the right length of steel where I can stand on it. You're right at the limit of elasticity. And you know, it should just be real solid. And we're gonna do the deflection too. This video is just going to be, hell yeah, just using equations. I mean, the equations are given. This is the equation for like how much that's going to sag. It's a sucky equation, but we can at least throw it in and get inches out of there and see if that's what we check on reality. All right, so holy hell, I feel like after this you're just like, nah, I don't believe you. But I want either. But that's why you have these check marks. You know what I mean? Places where you can get back to be like, nah, I'm not going to throw the towel in on everything. So my A for this is 3/4 is 0.75. I got to go 0.063. That's the thickness times 2, and then 0.75 minus that. That's my inside B. You know what I mean? So now you can just do this. You can go 1 divided by 12 parentheses alpha A to the 4th minus alpha B to the 4th. And oh, did I not put in alpha A? So alpha A is no, I didn't. So 3 divided by 4 stored as alpha A. Alpha B is good to go. So let's bring that equation up again. And hell yeah. So this is going to be my I. I'm going to store it as J. And then that other one for I, we got to store that as alpha I. And then this one we're going to store as alpha K. So let's do that. So we got alpha I, good to go, alpha J. And then this one, we got 0.5. This is ½ inch, stored as alpha A. 0.063 times 2, 0.5 minus that is, and that's going to be the inside width. So now we're going to do our equation. We already got it stored. And then booyah, we have and see how this number gets just even tinier. You know what I mean? It's not a factor. It's not going from this and then just being like, oh, maybe 4 times less, and then this, maybe like, you know what I mean, half of that. So we're going to store this as alpha K. Oh, whoa. We got to store that as alpha K. So now we're going to say, hey, what is alpha I divided by alpha J? It's 20. This is 28 times this. And now alpha J divided by alpha K. This is only 3.8 times. So yeah, I mean, once you get material, what this shape equation says is like, you know, it's a real fundamental of material mechanics. Get that material way out, and it's super rigid and can take a lot of strength, can take a lot of bending moment. You know what I mean? From that perspective, this is almost like wire. If I had it long enough, I could just bend it with my hands. Get this with that same. There's no way it would take 28 times, you know, that same kind of strength to do that. And then I divided by K, and this is 109. You know what I mean? The shape of this is like 109 times better than the shape of that. All right, so we have our values, and we're going to throw in 58,000 for our strength of steel, and now we can just go for it. You know what I mean? What do we want to find? This is 4 feet, so we're going to go 4 times 12, stored as alpha L. So all our units are matching. This Y is half the height. That's just 1. So if we're working with 2-inch steel, it's 1. But I definitely need to check on reality because so we're going to go 1 stored as alpha Y. But then we're going to go this 3 divided by 4 divided by 2. So half of that's going to store it as alpha Z. And then this ½ thing, half this height is 0.25, stored as alpha theta. So now we can just rock and roll. So we're going to see how much force could we, if this was 4 feet wide, how much force could we put on that? And so we're going to go 4 strength of steel, alpha I of steel, divided by alpha L, divided by 1. And we can put, on this one alone, we can put 1,807. So if this engine block only weighs 400, and we got 200 here and 200 there, hell yeah, if we made our table out of this, good to go. But remember how we were saying, like, hey, there's a factor of like 100? So yeah, we probably can't make our table out of that. And so I should have put this in view, you know, to make the movie cooler. But now we're going to do this one. So now we're going to go 4. And again, this 4 comes from just a beam that's not supported. You're just taking a chunk of wood, blocking it on both sides, standing on it nice and loose. You know what I mean? And you're just getting a pure, you know, it's just going to look like a smile. All right, hell yeah. So we got, we can do this kind of same thing, but what we're going to change, the I becomes J for this one, and then this 1 becomes alpha Z. And we get 100. Alright, hell yeah. So I don't know how much my camera cuts off at the end of the videos, but so we just did it. We did 4 times 58,000 pounds. We did the alpha, the moment of inertia of this one. That was stored as J. We divided by our length, alpha length of 48, so we're good to go there. And then we had to divide by half the height. So you're just getting even worse. You're taking the length, which sucks if it's long, and then you're, well. No. This actually helps. That's interesting. Like this eye, if this eye is big, hell yeah. But actually, when your diameters are less than 1, this kind of bumps it up again. But you know what I mean? It ain't helping, because you already took a number that's super tiny, and then you just took it to the 4th. You know what I mean? So that's way tinier than taking a big number to the 4th. Okay. And so yeah, we only get 176. So even this, making a table out of this is a no-go, but this was okay. You know what I mean? Visually, you might not see that. And obviously there's in between. You could do 1 inch. We're not going to do that today, because this is kind of what I brought out. And but that's cool. This, hella strong. This, a no-go for this. Well, just barely. This engine block weighs 400. By our calculation, we could take 176. So I don't know. You know what I mean? You do it. You do it. Make a good YouTube video. Just don't get anybody underneath that table. You know what I mean? So it could probably just barely work. And what we're doing is we're kind of talking about bracing this engine block underneath, so maybe the load is right in the middle. You know what I mean? And then so all the load is out on here. We're just saying, you know what I mean? Maybe this table doesn't have a sheet of plywood on it, and you're just throwing some runners this way, and obviously those are hella thick, but you just want to know if this will bend. You know what I mean? And that kind of makes the problem just a little bit easier. All right, so now, so that was that, and we already checked our shear. I guess we could check our shear for this. It's kind of a pretty easy calculation. So we got 0.063 is the thickness times times 4 times 0.75, which is one of the sides. So that's going to be the area times 58,000. So yeah, even if we welded this, you could hang 10,000 pounds off of it. That's crazy. And then obviously this one's going to be pretty good too. 0.063 times 4 times 0.5. And times 58,000 for the strength of steel, 7,000 pounds. All right, hell yeah. All right, so that's pretty much all you would need. But we have a new concept that comes up. That if this was real short, like obviously we've already did that one. You could put almost 40,000 pounds of compression, or you could hang something or pull this in tension with 40,000 pounds. And so that's kind of amazing. But if this gets tall, it kind of acts like a bow. You know what I mean? And there's fancy equations for that. You know what I mean? The second is just like, ooh, it's unstable, and then it's just going to do that, and you won't want anyone underneath there. So the equation for that is just an equation. You know what I mean? It's got like 4 different scenarios like the other one. And this is your best case, you know, firmly fixed. This is your worst case, the telephone. This is the flagpole where somebody climbs to the top and then they're like, whoa, this thing ain't strong. And then you got some in-betweens. And why not just use this one? You know what I mean? It looks like the bow. It's attached at the top, attached at the bottom, and it looks like a bow. Look at this. It kind of looks like it's attached to the bottom and attached to the top, so it might bow. And this is kind of your in-between. N is 1, so you're just taking this equation that says F is equal to pi squared EI divided by L squared. So that's what we got here. But guess what? What is pi squared? You know what I mean? It's like who cares? It's 9.86. Oh, my bad. I was, for whatever reason, I was thinking pi squared was just 1. I'm glad I ran that. So yeah, now we just have 10 over here. You know, it's good to double check your answers, but that's why I ran these. It's just like, well, if this is a product of the modulus of elasticity of wood and then the shape, well, the shape is just if it's square, it's just the factor of the length. Modulus of elasticity of wood, I can just factor that in, and you know what I mean. So I can do that for wood, and I can do that for steel. But heck yeah. So actually, so now we're going to do it, you know what I mean, I guess just from this equation. So we're going to go 10. Modulus of elasticity of steel is 29 million, also a good number to remember. 29 is half of 58, because 58,000 You know what I mean? And if you're in metric, 400 megapascals is your strength, and 200 gigapascals can be your modulus of elasticity. Now this is 20,000 megapascals, so you can see the difference, but you still kind of have that number as just you know, just half. So that can be a good check on reality. All right, so now we have our I for this, and now we're just good. So alpha E, I don't have that stored as anything, I don't think. So we're going to go 29 times 10 to the 6, stored as alpha E. And we're going to go 10, alpha E, alpha I for this. And then divided by, and this is alpha L, but we got to square it. So now in this case, the higher this length, wow, the crappier it gets. You know what I mean? For sure. And so, and then let's see what we get. So even with this at 4 feet, you know, it's so bomber. It's already 49,000 pounds. You know, ain't no thing. And so obviously you could make a deck out of this. If I saw a 2-inch tubing, like how high could we get? So now we can just go back to that equation and just kind of have some fun with it. And just start throwing in, it's got to be in inches, but let's go 240. You know what I mean? That would be 20 feet. So if it we could support 20,000 pounds, and the thing you're kind of shooting for in comparison is a 2x4. You know what I mean? Kind of the classic standard of holding up a wall every 16 inches is about 1,000 pounds. You should be able to get about 1,000 pounds out of that 2x4. And so if you put these steel runners, well, you could do them at widths of 32 inches. You know what I mean? Just over 2.5 feet. But that's probably not good enough. You'll probably have them every 4 feet. So you know what I mean? Hey, having these 20 feet long to support a deck also, you know, you would have to have kind of a lot of them because your force probably was going to be greater than 2,000 pounds. All right, so now let's do it for these. So now we use that kind of the same equation, but my I becomes the moment of inertia. That you know, the shape number. It's basically the shape and how much material is kind of outside and making it rigid. But all the material's in the middle, and almost like a wire in this one. So we're going to go alpha I goes to alpha J, and well, and is everything the same? Yeah, and hopefully we're doing it right. Pi squared, yeah, it's just 10. And EI divided by L squared. So yeah, so in this case, 4 feet isn't a big deal. You know what I mean? If you map this out as an equation, well, yeah, things go to crap at some point. You know what I mean? This thing blows up. Your length really screws things over on your force. But now let's go to this one and see if we could even make it out of that, and 4 feet's not gonna do this. Not gonna make it turn into an archer's bow. And what do we? Yeah. No. That was a different value. So we did I, J, and now we're at K. Okay, so we could do 450 pounds on each of these. And heck yeah, our thing only weighs 400 pounds. So even if our table was made out of that's pretty sweet. So currently, our check on reality is this member. You know what I mean? So actually, right now, we could make the legs out of this, and then did we say we could? I kind of forget. I would have to go back and look at the actual numbers that we saw. And wasn't this one? I forget if this one was sketchy and this one didn't work at all. But that's why we can just go back to the equation. Sigma is 58,000, so we're going to go 4 sigma alpha J divided by alpha L, and then we got to go this Z for this one. And is alpha Z? Yeah, is that. So yeah, we only get. Whoa. Yeah, let's see if we're doing things right. Let's go back to this one. So we got 4 sigma alpha I. Oh, you know what? Yeah, I'm getting bad at, I like this habit of doing divided by L, but I then got to go divided by Z. And so yeah, 176, so, and then this one must have been junk. Whoa. Oh, got to get more light. Alright, heck yeah. I have a hard time remembering what letters, so we got 4 sigma and then we got ijk, so this one's the k for our moment of inertia, divided by alpha L, divided by the theta for that one. And theta for this one is 0.25. That's just half the height. So this is 0.5 in diameter, half the height is 0.25. All right, so yeah, 176, 69, and so yeah, you could barely do this one. So right now you could do the legs out of this, and then you could do that. You know what I mean? So super sketch, and then you could put a 400-pound engine block resting on it. Now is that it? You know what I mean? At the end of the day, we're pretty close, because this other one for torque, and we already did a shear for like these, which is it's the same as a bolt. If you have a bolt, you know what I mean, it's still shearing over that area in that direction. But when we go to torque, we look at this equation. Well, it's similar. It's similar to this. You know, we have kind of a strength term, a strength term, a shape term, a shape term. This one we had a length. Well, when we're twisting on something, the max length is its, like, you know, kind of diameter. So let's see how that applies. It might be interesting if we put a diameter down here. And but then this has another length term. You know what I mean? Like half of, and this is interesting because this is length, and then you have a shape, and then you're taking half the height. But anyway, the reason why you don't have another, because this is force times distance. It's newtons times meters. You know what I mean? So we have one less length term in the down here. But you know, the same things to make things simple can apply. I mean, we can say that this is you know, stress. I mean, shear stress is just like tensile stress divided by 2 for steel. So 2 times the radius is the diameter, so you can just go tensile stress IP divided by the diameter, and you know what I mean? It's just kind of making life easy. And then what's IP? Well, just like this was, you know, like this was kind of the bending in one direction. But if we were rotating this in a circle, it would be, well, I don't want to say things I don't know, but if you're just bending a circle, heck yeah, you just take one of these. You know what I mean? And so this is for bending a circle. But you can, if you bend a circle this way and this way, it's the same. So up and then like sideways. And so the polar moment of inertia, kind of the shape number for a circle for twisting, is going to be both those together. And at the end of the day, just know that it's an equation, and we're going to plug and chug. So so it's pi d. It's pi d to the 4th divided by 32. So there you go. So if we do the torque, we got pi d to the 4th divided by 32. We're going to do a 1/2 inch bolt. So we got 0.5 stored as alpha d, and then I is going to be pi pi d to the 4th divided by 32. So we're going to store that as alpha h. So that's going to be our shape number for our torsion, just so we don't overlap variables. And yeah, so we have alpha O, which is our strength, alpha H, which is our I, and then we're going to divide it by D again. So, well, we already did it D to the 4th, so we could, you know what I mean, just do, you know, just do something like strength D to the 3rd. So what did we do? Heck yeah, D to the 4th divided by D is just strength pi D to the 3rd divided by 32. Well, guess what? Strength times pi, strength times pi divided by 32 is, no, so sorry. Pi divided by, what did I do here to get, so we're all good to here. And then, how would you simplify this? Oh, this is pound inches. But when you torque something in foot-pounds, you know what I mean? You have to take this diameter, you know what I mean, and change it to feet. So if you had 1 inch, you would go 12 inches downstairs, 1 foot upstairs. Well, now you're taking 1 divided by 12, and then you're taking that to the 3rd. You know what I mean? So inverse that. You're dividing by 1728, you know what I mean? So now this is input, my bad. Never mind. So yeah, some of these equations you have to be very specific about. I'm getting out pound-feet. I'm putting in PSI and inches, and then dividing by 122. So let's do that. Alpha D to the third, and then divide by 122. And so this is oh man, I just pulled these up from before, but we did this off a YouTube video. It was a 1/2 inch diameter, and oh, you know what? Yeah, in the video, the torque was a grade 8 bolt. So they were torquing a grade 8 bolt, which has a strength of 150,000, and you could put 100 foot-pounds on it. You know what I mean? And the braking strength. This is Engineering Farm or whatever. I forget the YouTube handle, but 100. No, it wasn't. I think it was like AVE. But anyway, 154 pounds was the braking. So then, if this is your braking stress, like it'd be interesting to have an equation for like, hey, I know the tensile stress, but I need to back it off by a factor of safety. So that's what this equation is. Even though I'm sure you just do not believe me that these equations have any validity. But it would be the same thing as not believing that pi r squared was the area. And then you'd be like, no, I don't believe you. I'm going to just measure all the squares, and that's what I've been doing forever. You know what I mean? Of a circle, and then I'm going to find the area that way. So there is some trust with equations, obviously. But there's just a lot of, I think you get the gist of, like, if I just went to the steel yard and brought my I-beam chart, I would just be like, hell yeah, I just want to know what the S, and because when you get I-beams, man, I mean, yes, you have a variety. You know, you have a variety of shapes, and some of the S's will kind of overlap. But then, yeah, you kind of, you know, there's only so many shape numbers for the I-beams, you know, and there's only so much overlap. So if you just get this shape number, and I like that it's called S, it's shape number, and I, it's like, hell yeah, I is definitely the shape. The shape of this is its moment of area. You know what I mean? The bigger the shape, yeah, I think you get it from that basic understanding. But it was just funny how this. I'm sure this is right in some way, but it doesn't even, for whatever reason, no, this was an interesting one, because you have to take that the moment of inertia of a square is a to the 4th divided by 12. So the moment of inertia of something looks at like this. Well, your height you get quite a bit out of, but your width, oh damn it, I don't even know. But if this is A and this is B, it's going to be, what is it, A cubed B divided by 12? I'd have to go back and look at that one. But yeah. I mean, if you have something like this, hell yeah, it's going to be strong. So if this is your A term, yeah, you get to cube that sucker. But then this way, you only get to do it once. So that's that. And then you still got something to the 4th divided by 12. All right, so we're almost basically there. Like obviously for well, let's do this torque one, just to make sure that if it's not a grade A bolt, what's our torque in pound inches? You know what I mean? Because that's what we're going to chisel out of this, and it's just fascinating because you have this quantity IP. It's pi d to the 4th divided by 32. I would have to look that one up every time, because if you're just taking a circle and then doing this, which you probably wouldn't do unless you have like wooden telephone poles that you're using as bridges. And so that's the other one I did. I was just like, hell yeah, I've got wooden telephone poles with a diameter, and I just want to know how many pounds I can get out of them. So we had a cabin that was like 40 feet long times 12. So we had 400. We had 480. And let's say we only had like 9. They were like 9 inches on one side. And I was just curious. So we're going to go 9 cubed times 2,000 divided by 480. So, but that was impressive. We could put. Hell yeah. So we could put 3,000 pounds on one of them, but man, they're old telephone poles. They got so many holes in them, and then just jumping on the bridge, man, it feels like you could break it. You know what I mean? So if it's fresh new wood, hell yeah. You know, if you got two of those, you could drive easily a car over it. But even at 3,000, like that's the cars weigh more than 3,000 pounds, and then we're saying this is the max, and that 9 inches of diameter, you know what I mean, it is fairly, you know, it's about 10 or 12 on the other side. But I just would never drive across that bridge. It's not even wide enough to do a car. But hell yeah, that's the beauty of having a cheat sheet full of equations, just to be like, I can go to the hardware store. Not with that one. That wrecked this video. Damn. But this was a bizarre one because I had to actually figure out how to get B and H in there as a ratio. So I could just be like, yep, there's B, that's H. And no, this makes sense, because if I did it the flat way, yes, the height gets squared, but the B doesn't. And I just don't know why a 2x4, so that's going to be 8 times 12, 96, 16.6 divided by that, and then multiply by 3.25, and then multiply by 1.5 squared. One pound. So there's something up with this equation. Yeah, it's definitely off. Huge. Yep, because even if I do the 2x4 the other way, which is, I think, I guess, is that what we're doing? Is that what we're doing here? So 3.25 to the third, and then times 16.6 divided by 12 times 8 for just a normal 2x4. Yeah, this equation just got wrecked. So I apologize there. But we have a check on reality. You know what I mean? That's what we have for this. So we have, let's do that. So we got 4 sigma I, and then we have Ly. And if I got this moment of inertia right, for a 2x4, we got 3.25. Let's do it this way, and 1.5. Am I getting that right? 2x4, 3 point. So we got 3.5. And so we get to do the 3.5 once, and we only get to do the 1.5 cubed. So we're going to go 1.5 cubed. That helps out, but then multiply by 3.5. So that's going to be our I. I'm going to store it as alpha G. Okay, so now we're going to take, and then half our height is 0.75, so we're going to type that in. And then we're going to just take a normal 2x4. So we got 4, so we got, and stress is there. So we got 4 times 58,000 times our moment of inertia divided by our length, which is 12 times 8, and then divided by half the height, which is 0.75. Oh my goodness. You know what I mean? Holy Toledo. Yeah, we got to put the strength of wood in here. So the strength of wood isn't 58,000. The strength of wood is 5,000. 5,000 for wood, 5,000 for concrete. Can't go wrong. You can bust wood up to 12,000 though. So let's type them in both. So yeah, this O term, yeah, the strength of wood is different than the strength of steel. So we have 5,000, and then that should do it. So a 2x4, if we stood on a 2x4, yeah, why isn't this working out? This is so interesting. So we have 4 times like 6,000 pounds per square inch. We have that moment of inertia. And let's just say you cut the 2x4 into a 1.5 by 1.5. So now you have 1.5 to the 4th divided by... Oh, did I not divide by 12? Yeah, I apologize. So yeah, we're so close. We're just making little errors. So this area moment of inertia for a square is a to the 4th divided by 12. So if you use this as your outline for what moment of inertia is, you know, you can do that. Hell yeah, this height is 1. So we got 1.5 to the cubed times 3.5 for the width, but then we got to divide by 12. So yeah, then that's a factor of 10 difference. So we're going to store that as alpha g. And then we're going to get 4 times 6,000. That's a fairly good number for wood. Times alpha g divided by 12 times 8 for a normal 2x4 divided by 0.75. Finally, for if you just take a 2x4 and then support it, you know, and use it, you can only put 328 pounds on it. And it's definitely going to feel, I think we've all done this. I think you can envision just an 8-foot stud, and standing on it is going to bend. It's not going to break. But yeah, it's got a max of 320. Compared to the other way, you know what I mean? It's, and I got to get more battery juice. Alright, heck yeah. So, got some more juice. And again, let's write this equation, because it's just a good one to have in your pocketbook. It's kind of hard to remember, like you would kind of have to write it down. But once you do, you just know that, hell yeah, at the end of the day, you just want to find the force of standing in the middle of a beam. I think that's fairly accurate, because if you stand on the edges, you know, obviously the bridge is strong, but if you stand right in the middle, yeah, that's probably where you want to know how many pounds you can put in the middle. You know what I mean? So this is like this case scenario. And so now when our 2x4 is this way, we got 3.5, 1.5. So we get to go 3.5 cubed times 1.5 divided by 12, and then we got it. 3.5 cubed times 1.5 divided by 12. Stored as alpha. We're going to store it as alpha f now. So we got 4 times 6,000 times alpha f for our area moment, divided by 12 times 8, and then divided by, in this case, half the height is 3.5 divided by 2. So that does reduce it, 3.5 divided by 2, but yeah, we get 765 pounds if you do a 2x4 that way. So 325, and then, I don't know, it's just fascinating. I guess you just double it, kind of, you know what I mean? But definitely stronger that way. And you know, I could have done something wrong, obviously, but we're just trying to fly through these. Yeah, that's the tricky beast right there, is like making sure you don't mess that number. Again, you know what I mean? With steel, finding something, you know, finding parameters that are just like given, you know what I mean? So do a 2x4, you know, this way and that way, and kind of memorize those numbers so you have that reference. So if you know, if you have something bigger than a 2x4, like a 2x8, you know, and you have it vertical this way, like you're using it for an actual, I forget the terms, but just, you know, joist or girder or whatever, that, like, hell yeah, your I value, that shape number is going to be way bigger, you know what I mean? And that influences how much force you could probably put in the middle. And again, this is just kind of like an ideal scenario where, hell yeah, if I had a bridge, I want to know how much force I could put in the middle. That's going to be the weakest part. Okay, so I think we did it on this one. So now what we're going to do is I'm going to take these two shapes. So we're going to take these two shapes. We're going to use hopefully the one equation that we're okay with using, 4 sigma I divided by Ly. You know what I mean? And alpha I for this one, we still got that in. Alpha J, cool, we got that one in alpha K. And just to make sure, we got I divided by J, that's that 28. I divided by K, that's 109. Alright, hell yeah. So this week, I've been having to double check the letters because in my calculator. Sometimes I switch the letters out, and man, that was a bugger when that causes miscalculations. I definitely know they're miscalculations. It's just impossible to find where they popped up when you're just throwing the same numbers. And then, you know what I mean? So I'm going to store this as alpha O, and obviously this is going to be J and K for this one. This is J, this is K, and then our length. Well, our length is what we want to find. So I have a bunch of lengths of this steel, you know, out in the garages. And so Now I want to know what length I know how much I weigh. I'm going to stand in the middle of them. So we need to rearrange this equation for length. All we got to do is bring the length upstairs, force downstairs. So we got length is equal to 4 sigma I force y. So 160 stored as alpha F. So now, so we have our weight, we have our strength of steel, and we have this as J and K. And then this value, this is going to be that 3/4 divided by 2. So that's going to that's Z. So we have this value for Z. Those two relate. And then this is stored as that theta letter. Okay, so now we can just bust this out. We can go 4 alpha O, alpha J for this one. This is the one we're going to do. Divided by F, divided by Z. And heck yeah. And then for this one, and we only get 53 inches, you know what I mean? So this one, we can only have something that's about 4 feet, a little more than 4 feet. And when I stand on it, we're going to be A-okay. But it's going to be right at that limit, you know what I mean? It's going to be right at that elastic limit. We're saying, hey, if we stand on it with 53 pounds in the middle, like the moment is going to put max stress in this, you know what I mean? It's going to put a 58,000 pound force on the top and bottom. The top in compression as it does a smiley face, and then the bottom is going to lengthen. And it's just fascinating. That's what's happening inside the steel. But steel can hold that. So the second I step off, you know what I mean? When I do the whole pool trick of making sure my pool cue isn't totally bent, it shouldn't. Every molecule should have gone back to the same location. Okay, so now we're going to do this one. We have a moment of inertia of K, and then that theta. So K is hella small, but hey, this theta kind of dividing by a smaller number kind of helps out. But we get 20 inches. I have to figure out what we're actually calculating. So we have 53 inches, and I'm going to say this is 21 inches. All right, hell yeah. So the next part of this video, I'm going to find a 53-inch chunk of this and a 21-inch chunk of this, and we're going to stand on it, and guess what? Nothing's going to happen. You know what I mean? It's not going to be an exciting video. I'll make a disclaimer at the beginning. Go to the end right now, because this is where the magic happens. But this is going to be one of those videos that's going to be lackluster. But that's engineering. You want things to be lackluster. We have this, you know what I mean, kind of force change in length curve, you know what I mean, or strength stretch curve, and we want to operate in here. Things are going to bend a little bit. We are going to lengthen things when we tug on them. When we apply kind of the max force. But as long as we stay within this line, when we let go of the force, when I step off this, every molecule will go back to the same location. You put more than that, well, yeah, then we get a permanent, and then hey, it's like it's permanently stretched just by this much. It's permanently deformed, you know. Now it looks like a smiley face. All right, without further ado, 53 inches, 21 inches. Catch you on the flip side. Alright, hell yeah. It's barely to the edge. This is going to get sketchy. But let's see if we can put our weight on it. Okay, I can definitely feel it bending, for sure. This feels like the max, you know what I mean? It definitely settled in, and so that's pretty good. But it's holding, you know what I mean? If this was a rung on a ladder crossing a crevasse in Everest, yeah, it'd be okay. Definitely more area, more moment, though, for sure. All right, let's step off this. Whew. And heck yeah, it definitely is a little bit bent, though. I can definitely see this a little bit bent. Alright, hell yeah. So we got the 53-inch, and this is 3/4, you know what I mean, right to the edge. Now this thing is already a little bit bowed, so, you know what I mean, I think it's still, I didn't put it the strong way, I put it the weak way, but we'll just see how much deflection we get. Yeah, it definitely sags in. Oh Oh yeah, yeah. So it's right at the limit, and it is bending for sure. You know what I mean? So this will be permanently bent. You know what I mean? And so yeah, there you have it. I was surprised. I thought the equations were going to be a little bit stronger actually. But you know what I mean? Our moment, that moment equation really does it. So you don't have steel at the very corners. It's a rounded tube. You know what I mean? So yes, the force is going to be less than calculated. But heck yeah, we're balancing on it. And so there you go. I know it's not the best view. We'll try to get a close-up. Okay, but yeah, this thing's permanently bent. And so yeah, because what I did is I brought a longer piece just to see how much you could go, but no. So this held, but it is bent. So it passed the modulus. You know what I mean? It passed the yield stress. So some part of this got more stressed, and then has a permanent change in length. So anyway, so it definitely wasn't linearly elastic for that one. Alright, hell yeah. Alright, hell yeah, thanks for joining me. Now, that was a huge amount of deflection, but we can't use the deflection equation because it wasn't linearly elastic. Like, this piece didn't go back to the original shape. Like, it's permanently bent. So at some point, you can put a force in there, measure the deflection, and then back off, and every molecule is going to go back to the original shape. Obviously, we didn't see that, so if we do get deformation, that equation doesn't apply. All right, so we won't dive into that one, but heck yeah. So thanks for joining me, and that's a video.